Today we're going to talk about what is possibly the most important topic in the entire semester. Okay, so this is maybe the most important lecture for the whole semester, because we're going to talk about what we call the momentum principle, which relates quantitatively relates to change of momentum of a system to a quantitative measure of the interaction of the system with its surroundings. It's a fundamental principle because it applies to everything. It applies to atoms and it applies to galaxies and supernovas. It is always true. There are no exceptions to it. So it's not a special case thing. It's truly, truly fundamental. So this is our first fundamental principle. We'll be talking about 3 fundamental principles this semester, or maybe 4, depending on how you count. We're going to talk about the momentum principle. Later, we'll get to the energy principle and then the angular momentum principle. And finally, another thing related to energy, which is the fundamental assumption of statistical mechanics, or also which leads to the second law of thermodynamics. So that's the space we're operating in. So we finally have enough background to get to our first fundamental principle today. So we'll start applying that. So we found last time that interactions if we divide the world into system and surroundings, which is a very important distinction that is sort of key to all the analysis we're going to be doing this semester. We saw that the change in motion of a system was due to interactions with surroundings, but that the amount of interaction required to change motion depended not just on the velocity of a system, but also on its mass. So we defined momentum as the quantity mass times velocity times this factor gamma, this relativistic factor gamma, which is equal to 1 over the square root of 1 minus the ratio of the speed of the object to the speed of light, quantity squared, times m times v. And we also established by calculating gamma at various speeds that we could approximate gamma at 1 unless the speed got to be a significant fraction of the speed of light, like half or more of the speed of light. So we'll often be using the approximation momentum is equal to mass times velocity, momentum being a vector because we're multiplying velocity vector by a scalar mass. And we talked about the idea here that we would see qualitatively we'd see that what we're interested in is changes in momentum, because constant momentum is really boring. Something's traveling in a straight line at constant speed and nothing's happening. What's interesting is when the motion changes due to an interaction with the surroundings. And so we're interested in changes in motion, in momentum. And in fact, we're interested in this because if we can figure out how momentum is going to change, we can predict the motion of a system into the future, no matter what it's interacting with. And so we said qualitatively we had the momentum of a system at a short time in the future depended on 2 things. So we have a checklist. It depends on the momentum right now. Let me write this more clearly. Momentum in the future depends on the momentum right now. And it also depends on interactions with the surroundings, which we quantitatively express as a net force times a short time delta t, the time over which the interaction occurs. And so we find that the momentum in the future, a short time in the future, depends on the momentum now, and it also depends on the net force acting on it. And this quantity has a name, it's called impulse. So we could say this is the net impulse. And mathematically, we can write this as a simple sum, it turns out. So we can write that the momentum of a system at some short time in the future is equal to the sum of its momentum now, which is a vector, plus the net impulse acting on it. So the net force, which is a quantitative measure of interaction with the surroundings, times delta t. And this is one way to write the momentum principle. And this is another of these equations that you need to know. You need to memorize it. So let's figure out what it means. What's a force? Well, a force is a quantitative measure of interaction. Sometimes people talk about it as a push or a pull, something that changes motion. It's a measure of interaction. And how do you measure forces? We have to have some standard for measuring forces. Well, the simplest way to measure, one simple way to measure forces is to use a spring as a tool for measuring forces. So if we take a spring and we attach it to a wall and we pull on it with some amount of force F, the spring stretches. And so what we get is the spring is longer. So here's the stretch. And it turns out the amount of, for a spring, as long as you haven't stretched it enough to break it, the amount of stretch of the spring is directly proportional to the force. So we could build a scale out of springs, and we could measure different forces by seeing how much they stretched a spring. So that's one way to come up with a system of measuring and comparing the magnitude of forces. Stretch, so the stretch is proportional to the magnitude of the force. We're working in SI units, and so the units of force are newtons. Named after Isaac Newton, the famous 17th century English physicist. And the abbreviation for Newton is N. And let's see how the units here in this equation work out. We know that momentum must have units of kilograms times meters per second. So that's the units of momentum. So this is kilograms meters per second, kilogram meters per second. So this quantity must end up, this is obviously newtons times seconds, but a newton times a second must equal a kilogram meter per second. So it looks like a newton could be expressed as a kilogram times meters per second squared. And we'll see as we go along that there are really only two kinds of forces that will be that exist, that we'll be working with. There are forces that act at a distance. So you know one, right? The gravitational force. So two massive objects can attract each other even if they're far away. The sun attracts the Earth, and it's 8 light minutes away. Electric forces are also like that. There are forces that require things to touch, and we call those contact forces. And we'll see that some of these contact forces are actually just the combination of electric forces of lots of little particles interacting with each other, the atoms and protons and electrons of which all matter is made. But that there's some fundamental forces like the strong force that holds nucleons together in a nucleus that actually basically are a contact force and requires these things to be touching. And that's all there are. There are only those two kinds of forces. So the momentum principle is our first fundamental principle. Now notice that this is a vector equation. So we have momentum. I like to say the momentum in the future is the momentum now plus the net force. What does net mean? Well, what net means is total. It's total. It's the sum of all the forces acting on something. And since forces have directions, so we note that force is a vector. If we had an object here, our system, and we had one force, we'll call it F1 acting up, and we had another force F2, acting that way. Okay, Alexander, hang on. Well, that's an interesting question. To get the net force, we have to add F1 plus F2, and we know how to do that graphically, right? We know how to add vectors. So we're going to redraw these forces. Here's F1, and then we're going to take F2 and put the tail of F2 at the tip of F1. And then we're going to draw the resultant force starting at the tail of that vector and going there. So this is our F net equals F1 plus F2. So the net force acting on this object is the sum of those two forces, and that would be F net. So Alexander asked an interesting question. What is the second squared doing in there, and how does that relate to the flow of time? Why is there a second squared? So we have kilograms times meters per second squared here. What does that actually mean? What it really means is it's a second derivative. And it's a rate. So meters per second, that's a unit of speed, right? So that's V. And we saw that velocity was actually a derivative. It was the rate of change of position. And we could approximate it as a change in position over a time interval. So we have meters here at the top and, delta t, and seconds here at the bottom. So that's a rate of change of position. It changes if your speed is 1 meter per second, your position is changing at a rate of 1 meter per second. Well, if your speed is changing, so we have dv dt, that's the derivative with respect to time of dr dt. Or the the second derivative of position with respect to time. And so it changes at the rate of a meter per second, say. So it's a rate of change, and that's why we have all those seconds in there. Does that make sense? So one other thing to note about this equation for the momentum principle is that we can also write it, by the way, we could use the subscripts final and initial if we wanted to. So we could say final and initial. I like to say in the future and now because it makes it very clear what we're doing. We're predicting a change here with this equation. So this equation, momentum future, is equal to the momentum now plus F net delta T. It's a vector equation, so it really actually has three separate equations here, one for each component. So we write P, the momentum is, the X has an X component, a Y component, and a Z component. And force has an X component, a Y component, and a Z component. And so we actually have three equations here. P future X is P future, is P now X, plus F net X delta T. P future Y is P now Y plus F net Y delta T. And P future Z is P now Z plus F net Z delta T. Now, sometimes what's not in an equation is actually as important as what's in an equation. And so if we look at this equation for the change of an X component of momentum, we notice that, interestingly, this only depends on the X component of the force. And the X component of the current momentum. It does not depend on the Y component of the force or the Z component of the force, which tells us that a force in the Y direction can only change the Y component of momentum. It can only speed something up or slow it down in the Y direction. And it's never going to make it change, turn, or do anything else. A force acting in the X direction only affects the X component of momentum, which suggests to us, so this is fairly deep, and it has a lot of implications that we're going to sort of need to work through as we go along. But it suggests correctly that if something's going along with momentum only in the X direction, and we apply a force in the minus Y direction, that force is not going to change the X component of the momentum. So it's going to keep going along. It's going to have a new momentum. So its new momentum, P future, has the same X component. Now it's got some Y component, and so the net momentum is going to be the sum of those two things. But this X component remained unchanged. We just added a non-zero Y component. So this vector equation really tells us a lot about how we understand these forces to work. Yes, vectors are vectors. They work the same way. So Marco says, does it work the same way as velocity vectors? And in the sense that the x component of velocity only affects the x component of position, and the y component of velocity only affects the y component of position, that's absolutely correct. So we can also rewrite this equation, this momentum principle equation, as by subtracting momentum now from both sides. So if we do this, we get P future minus momentum now is equal to what we're going to call the net impulse, the net force divided by times delta t. And of course, we could write that as a delta p, a change in momentum. So we could write delta p is F net delta t. And that's exactly the same equation. We've just rearranged it algebraically, and sometimes it's useful to think about it this way, and sometimes it's useful to think about it the other way. And you probably may also have thought that if, suppose we divided both sides by delta t, so delta p over delta t gives us the net force, and that sure looks like a derivative, and it is, of course. So in the limit as delta t gets small, we have the rate of change of momentum with respect to time is the limit as delta t goes to 0 of that out net. Now, sometimes we can use that derivative form, but a lot of the time it's very convenient to actually use this finite difference form to allow us to predict step by step what's going to happen. It's particularly useful when we don't have a constant force, when the interaction with the surroundings is changing, and we have to keep changing the force. So we have to keep taking small steps and changing the force. So this way of writing the momentum principle is a good way to write it as long as delta t is small enough. So what does small enough mean? Small enough that F net is approximately constant over that interval delta t. Now we can use this equation to predict the motion of a baseball, say. So suppose that that we have an initial momentum of 0.003 kilogram meters per second. So we've already calculated the momentum by multiplying the mass of the baseball times its velocity. And that we have an impulse, F net delta t, acting on it of -2 to -4 Newton seconds. We can get its new momentum is just going to be its original momentum plus the net impulse, -2 to -4. Which is going to equal -2 to -1 kilogram meters per second. And what can we do with that? Well, we know the mass of a baseball, which I don't remember off the top of my head, but we'll say it's, what does a baseball weigh? 1/3 of a pound? So 1/6 of a, well, we'll say it weighs 0.3 kilograms. I don't actually know that. Then that would mean that we could say its final speed, final velocity is going to be final momentum divided by its mass. So here's a question to think about. If we have a basketball that's falling straight down, so that's the initial momentum, bounces on the floor and it rebounds straight back up, what is the direction of the net impulse that acted on this basketball? So you should see a pole, and the pole has to do with the directions of those green arrows. All right, let's see what you said. Again, notice that the red line is just the majority, not a correct, not necessarily a correct answer. In this case, though, it looks like it is correct. And so noticing, and how do we get that? Well, the change of momentum, one way is to think about the change of momentum being equal to F net delta t, the net impulse. This is a vector equation, and it says that the direction of delta p, the change in momentum, has to be equal to the direction of F net delta t, which is the direction of the net impulse. And so remember, subtracting collinear vectors, so we have P final and P initial, and we want to subtract them, so we have to put them tail to tail. And now we draw delta P starting at the tip of the initial and going to the tip of the final vector, and I'm just going to draw it off to the side here so that I'm not writing on top of what I've got. So we find that the change in momentum is upward, and therefore we conclude, we deduce here that the net impulse was also upward. So F net delta t is also upward. Okay. Now, so do you have what questions do you have about this? Now, there's some very interesting implications of this momentum principle that aren't necessarily obvious. And they're also something that make it possible to do these predictions that we're wanting to do. And this equation tells us that the entire history of an object is contained, up to this moment, is contained in its momentum now. And we can think through this in the example here of a tennis racket hitting a tennis ball. Suppose the tennis ball is initially at rest here in this first image at time t equals 0. And so its momentum at that point is zero vector, and the racket exerts a force in the direction shown by the red arrow. Okay, so there's an impulse in that direction, and so this tennis ball gains, during a short time interval, delta t, this tennis ball gains some momentum in the direction of the impulse. So when we get to a time later, a time t plus delta t, t0 plus delta t, the momentum of the ball reflects the force that was exerted on it a moment ago. The angle of the racket's changed, and so it's now exerting a force in a somewhat different direction. So that's going to modify this this momentum now, there's going to be an impulse in this direction, in the direction of the red arrow. So we would add that delta P here in a slightly different direction. Let me draw it in a better way. And now the momentum of that we say that force acts for a short time. Now the momentum of the tennis ball reflects its experience in the past 2 delta T time steps. And now the racket is exerting a force in a different direction. And so we have an impulse that way. And so forth until eventually the ball loses contact with the racket. And this momentum now is actually the sum of all the impulses, over little times that the tennis racket exerted on this ball over this whole time. So the entire history of this tennis ball, all the things it's experienced are added up into its momentum now. And that means to predict its motion, we don't need to know the details of its interaction with the racket. We actually don't even need to know that it did interact with a racket. Maybe it just got bounced off the ground. Maybe something else happened. We don't need to know its history. All we need to know is its momentum now and whatever force is acting on it now. And we're going to be able to predict its future motion. So the racket is no longer touching it. So it's no longer in contact with it. The racket is no longer exerting a force on the tennis ball. Wasn't it important that it interacted with the racket? Absolutely. It probably wouldn't be where it is with the momentum it has now if it hadn't interacted, but it's all added up into the momentum now, so we don't need to know about that. And that's a very powerful idea. There's some other things to think about here as well. Let's think about this. You want to push a book across a table in such a way that its momentum remains constant. The book is already moving. Which statement describes the force you must exert over one time step? So 1 is you don't need to exert a force at all because P future has to be the same as P now. The force you exert must be exactly equal in magnitude to the friction force by the table because P future must be the same as P now. The net force on the book has to be 0. Or you have to exert a force on the book that's actually greater than the force by the table. So think about the momentum principle. When you're thinking about this, try to actually apply the momentum principle. So it's impossible not to guess, right? But then go beyond that and actually try to apply the momentum principle and see what it says. And in this case, the majority is not right. And let's see why not. So the answer is 2. And let's see why, according to the momentum principle, this is the answer and not 3. So let's write down the momentum principle here. It says P future is P now plus F net delta T. And if the momentum is changing over some time interval delta, if the momentum is constant over some time interval delta T, this must mean that the momentum after 1/10 of a second is exactly equal to the momentum it has right now, right? So this quantity has to be 0. Now, it's really easy when thinking about a situation like this to focus on what you're doing instead of what all the pieces of the surroundings are doing. But what F net means is, it means due to everything. And the table, the book is interacting with many things, the air, the table, your hand, but the key pieces are clearly going to be the table, which is exerting a friction force on the book, and your hand. Okay, Joseph, you're close. Let's wait. Let's get through that, and then we'll address your formulation of it. You've got a nugget of truth in there. So here the net force has to be 0. So if we draw a diagram, here's our book. Physicists always represent a system with a dot. Let's say you're pushing it in the well, let's label it F by U. You're pushing in that direction. The table is exerting a friction force in the other direction. And so the momentum principle tells us that if the momentum isn't changing, if the future momentum is equal to the momentum now, that the net force exerted over a time interval delta t has to be 0. And the only way to do that, so we can rewrite our equation here. So P future is momentum now plus force by U plus force by the table times delta t. It says that the force by U must be exactly equal to the force by the table and opposite in direction, so they add up to 0. So if we add these two forces by putting them tip to tail, we have F table, and then we add to it F by U, and the vector we draw from the tip of the tail of F table to the tip of F by U is of 0 length. What would happen if you exerted a greater force than the friction force? What would happen if this was true? Well, if the force by U was, that's exactly right, it would speed up, wouldn't it? So if the force by U was greater, the net force, so here's the force by the table. If the force by U is greater, then here's the net force, and the object is going to speed up. So we have to, so you think you have to push hard to keep the book moving, and you do, but you're pushing only exactly as hard as the force the table exerts backwards, and not harder, because if you push any harder, it's going to actually speed up. So to keep it moving at constant speed, you have to. Now, Joseph's question is an interesting one. He asks, what can if there's a non-zero net force, what can we conclude, basically, is his question. And that's another way of asking it. So non-zero F net. And the answer is that what happens depends on two things. This is, and so we're back to our checklist. Are the momentum, a short time in the future depends on the momentum now and the net impulse. So so it depends on the momentum now. So here is the momentum now. If the net force is in the same direction, then we're just going to add a little impulse, F net delta t, and increase the magnitude of the momentum. If the net force is in the opposite direction, we would slow it down. So we decrease the magnitude. But if the net force is in a different direction, so here's our momentum. If the net force is in a different direction, in fact, if it's perpendicular to the momentum, it actually ends up changing the direction of the momentum. And if it's a combination of those, so the new momentum, so we've got a F net delta t, it's gonna turn the momentum here. And of course, if a force has components that are both parallel and perpendicular, so it's like that, then it would speed it up a little bit. The F net delta t is in that direction, and so it would speed it up a little bit and turn it. P future. Now notice also, so that's an important distinction, and we'll see that in the limit of very small delta t, as delta t gets very small, a force perpendicular to the momentum only turns the momentum. It doesn't actually change its magnitude. So let's actually look at an example of a situation like that, kind of jumping ahead a little bit. So let me show you a GlowScript program that actually applies the momentum. So this is a VPython program that applies the momentum principle to the system of the Earth as it's affected by the sun. So the little green dot here is the Earth. The yellow sphere is obviously the sun. And this blue arrow is, okay, so Kevin asks, that's why the basketball's F net is not down, even though gravity is slowing it down the short amount of time. Yes, Kevin, that's exactly right. And that's a really good point, that the situation we talked about with the basketball bouncing off the floor, what we were doing is we were looking at what physicists call a collision. And a collision involves large forces for a short amount of time. So what we did is we took a time interval just before the basketball touched the floor to just after it touched the floor. And during that time, the most important force acting on it was the floor. And the basketball came down with momentum P, bounced off it, and went up with momentum that had almost the same magnitude, but just had changed in direction. And that's why we conclude that during that short time interval, the net force acting on it has to have been up. The net impulse was up. Even though you're absolutely right, Kevin, if we let it go longer, the force due to the Earth acting down will slow it down. So let's look here at, so this is a a program like one you're going to be able to write later on that models the interaction of the Earth with the sun. And so the blue arrows are momentum, and a red arrow is going to be a force. And what we're going to do is we're going to see what would happen, what the momentum principle would predict the path of the Earth would be near the sun if we use the force, the gravitational force exerted by the sun on the Earth. Now, you can't calculate that yet, but we'll get there. But what you do know is that a gravitational force is attractive, and it acts along the line between two objects. So the Earth is always going to be attracted toward the sun. So, so here's its current momentum. That's momentum now. And if we calculate the gravitational force, we show it by this little red arrow here. And it points from, it pulls the Earth toward the sun. And therefore, this blue arrow, this pale blue arrow up here at the tip is delta P. That's our impulse, F net delta T, acting for our time interval. What's our time interval? Well, we've chosen 1 month as our time step here. It takes the Earth 12 months to go around the sun, right? So so we add those two vectors to get the new momentum. And then we do what we did last time, which is we say, well, from the momentum we can get velocity, and from the velocity we can predict the new position of the Earth a month from now. So we're going to use this dark blue arrow as the new momentum, and we're going to let the Earth move, applying the position update equation. And now it's in a different position. So now what do? We only know what's going to happen in a month. Well, we do it again. And this is called iteration. So we do the same calculation over and over again with the new values. And that's what meant by an iterative calculation. So we calculate the force, and now the force has changed direction because the Earth is in a different position. And so we have an impulse F net delta T in the same direction as the force. We add that to the momentum now to get the momentum in the future. We use that to get the average velocity, and it moves that way. We use the position update equation to move it. And now we get to do it again. This is why it's nice to have a computer doing it, because after a while it gets tedious to do all these calculations. So we calculate the new force, we calculate the impulse, we calculate the sum of these things to get the momentum now. We have the momentum, we use that to get the new position, and we do it again. Force, impulse, new momentum, velocity, position, force, impulse, new momentum, velocity, position. So you can see that we're getting kind of what we expected. It's kind of orbiting here. But does it really look like we expect the orbit to look? First of all, we don't think the Earth moves in these jerky straight lines. And second, it looks like it's getting a lot farther away from the sun. It turns out the Earth's orbit around the sun is very close to a circle. It's only a teeny bit elliptical, distorted from a circle. So this is a very elliptical path. So what could we do you think, to improve this prediction? Shorter time interval. Okay, so remember that our statement of the momentum principle, so P final is P initial plus F net delta T, was for delta T sufficiently small that the net force didn't change very much. So we won't worry about derivatives yet, let's actually just try taking a smaller delta T. So let's make it 1 day, okay? And now I don't need to click because I'd have to click 365 times to get it to go around. But we can see that we're still taking finite steps. We're still moving in these little tiny delta t steps. But moving 1 day at a time produces an orbit that looks completely circular, that looks very smooth. So we found delta t short enough that this prediction works well. Now, an interesting thing to see here, and this goes back to the question somebody asked earlier about what forces do. We have a case now where the force acting on the Earth is always pointing toward the sun, so it's always changing direction. The momentum of the sun is tangent to the Earth is tangent to its path here. So we have a case where in this very special orbit, a special circular orbit, and most orbits aren't circular, the net force, and therefore the net impulse, is always perpendicular to momentum. And you can see that what it's doing is turning the momentum, but not changing its magnitude. So it's not speeding it up, it's not slowing it down, it's simply changing its direction. All that centripetal force means, Parker, is that a force acting toward the center of something. And we're going to want to be more precise than that. So we're going to talk about forces that in terms of the object and the surroundings that is responsible for them. So all centripetal means is a fancy word for happens to be pointing toward the center of something. We're going to talk about this as the gravitational force by the Earth, so that we know exactly what's responsible for this force. Yeah, that's right, Alexander. So we're not really taking, I mean, in our calculation, of course, in the real world, nature really is sort of taking a derivative here, but in our calculation, we're taking actually pretty finite steps. We're taking steps of an entire day, 24 hours, many minutes, many seconds, right? 24 times 60 times 60 seconds in our step. And we're still getting a very smooth circular orbit, so that approximation is actually good enough. So Melinda, centrifugal force would mean it comes from the Greek centra, it means the center, and fugal means to flee. So it would be a force away from the center. And so if there were let me stop this. If there were a force acting, a centrifugal force acting, it would actually be acting in a direction opposite to that red arrow. And it doesn't exist. If somebody taught you about centrifugal force, it's actually a mathematical trick that works in one particular situation to get something, but is actually not a very general thing. Other questions about this? You've been asking great questions here. So Parker's description of centrifugal force is actually pretty good. All right. So let's go back to pencil and paper, or the modern incarnation of pencil and paper, which is one note and a touch screen, and talk about one thing we're doing in these calculations. So our iterative prediction of motion here. So iterative prediction of motion, when the net force is not zero and the momentum is changing, we pick a delta t small enough that the net force, which is the sum of all the forces, is approximately constant. And we do basically 3 steps. First, we calculate the net force, so we find the net force. And then we update the momentum. So F net is F1 plus F2 plus whatever. Update momentum, so we have momentum in the future is the current momentum plus the net impulse, F net delta T. Update is clearly one word. We update the position. So final position is the position now plus V average delta T. And now that things have moved, the forces have changed. So we have to go back and do this again. So we repeat, we iterate. What differentiates momentum from force is that an object can have momentum is inherent in the motion of an object. So a motion can have momentum with no force acting on it at all. In outer space, if we have a rock traveling at some velocity and it's far from other objects, it has a momentum, and momentum is its mass times its velocity. It will go forever with that momentum. Forces are irrelevant. What a force does, and notice the forces have different units for momentum for a reason, but what a force does is it can alter momentum, and really a force is just a quantitative measure of interactions with the surroundings. Interactions with the surroundings are what change the momentum of an object. So a force can, applied over time, can change the momentum of an object, but it's not the same thing as momentum. This is really a causal relationship. So if we write it as a momentum is a property of an object, yes, that's a very good way to say it, Mitch. Momentum is a property of an object, whereas a force alters momentum in an interaction. That's exactly right. So if we write it as delta P is F net delta T, this is the cause of a change, and this change is the effect. So this equation doesn't say they're the same thing. This is yet another interpretation of the equal sign here. This equal sign really gives us a causal relationship. This is interaction with surroundings, and this is the change in motion. So it's cause and effect, and this is a good way to be thinking about it. Now, one interesting thing about this calculation we're doing here is what we used as an approximation for the average velocity. What we actually used was the approximation V average is approximately equal to the final momentum over the mass of the object, or the future momentum. And at first you might think that's not a very good approximation. Why use that instead of taking, so why not P final plus P initial divided by 2? And then divided by the mass. And the answer is most of the time it's not a very good approximation, oddly enough, because most of the time we're going to be in a situation where forces are not constant. And this works for constant force because that changes V linearly for time. So suppose, let's talk about one dimension. If the y component of velocity is changing linearly with time, then if we took these two time intervals and averaged them. We took the velocity here, the Vy here and Vy here. The average would be there, and that would be a good average. But in fact, that's often not the case. So suppose that V sub y did something like this with time. And we said, well, we're interested in the average y component of velocity between time t1 and time t2. So what we would be averaging is that value and that value. So we would get an average value for V, which is, if we took, this is Vy initial plus Vy final over 2. But that, in fact, is actually really nowhere near what the actual average velocity is. You know, a much better approximation to Vy is somewhere here. So So in fact, using this approximation but taking delta t short enough is actually computationally a very effective way to do it. The other thing that matters here is the order in which we do these operations. This is numerical integration. So we're adding up, because an integral is just a sum. And so we're adding up the effects of applied forces over step by step. We're integrating numerically with respect to t. But it isn't just simple Euler integration. It's called Euler-Kromer integration, for those of you who are interested in you don't need to know this. But if you're interested. And the fact that you have to update momentum before you update position means that you get very good results in your iterative calculations. Orbits close, springs oscillate correctly, and whatnot. We have a few minutes, so first of all, what other questions do you have? Let's take an example of kicking a ball on the moon and just quickly do an iterative step. Do we have time to do that? We don't have time to do that. But the basic idea would be, if we knew the gravitational force acting on a ball on the moon, and it's different from the gravitational force acting on the same ball on the Earth, so it would actually be equal to, we'll see in chapter 3 where this comes from, but it's going to be equal to the mass of the ball times the magnitude of the gravitational field on the moon, which is actually times 1.6 newtons per kilogram, and it's in the minus y direction, 0. And so if the ball was, we would actually just take the ball's initial momentum, add that force times delta t, get a final momentum, use that to get a velocity, and use that to get a position. Well, so Mitch, let me get back to Alexander in a minute. Mitch asks, why did I write this expression? And I was asking the question, in our calculation here, what we're using as an approximation for the average velocity is we're taking this future momentum and dividing by the mass. And the question was, why are you not just averaging P future and P now to get it, and then dividing by the mass to get an approximation for the average velocity. And the reason is it doesn't work very well in any situation except a very special situation where a force is actually completely constant. So this approximation where we, in our iterative calculation, we approximate the average velocity as the final momentum over mass, turns out to work better. So Alexander asks, at what point is it necessary to move from a really good approximation to more exact modeling? And that's a pretty interesting question, because the answer is sometimes it's important to try to be exact, and if you can use calculus or something, that's fine. Unfortunately, most real-world situations, that's not possible. And so, interestingly, although it is possible to model by doing a lot of horrible algebra, it's possible to model the interaction of the gravitational interaction of, say, a satellite, a space probe, say, if we have the Earth and a satellite, we can do that analytically meaning algebraically. However, you add one more object. So this is our system. This is part of the surroundings. You add one more object, let's add the moon, and you can't do it. It's that simple. There is no algebraic solution or calculus solution. And therefore, this iterative approach with a finite difference is actually the most general approach we can take, which is why we're learning it. And if you have a question, why don't you, since everyone's typing, why don't you just go ahead and unmute your mic and ask it.
So whenever you put in that force vector that you wrote, and you put 1.6, now down at the bottom where you're writing.
This one, that's just on the moon.
Could you, I was gonna ask about the units, because you put newtons per kilogram. Could you write it just as meters per second squared also, or?
Yes, it does work out to that, right? Because we saw up here, way back up here, that the units of, so a newton was a kilogram meter per second squared. And so newton per kilogram would be newton kilogram meter per second squared divided by kilograms, and that would, we will use newtons per kilogram because it's actually kind of a fundamental way of thinking about a force.
Okay. So, but any time you're using momentum, though, you're gonna write the full units out, kilogram meters per second squared.
The units of momentum are kilogram meters per second. So momentum is because it's just think it's mass times velocity times.
Oh, okay, yeah.
Right. So that's kilogram meters per second. The units of force are newtons, which is, and since an impulse is F delta T, and that's seconds, then the units of newtons have to work out right. So units of newtons have to be kilogram meters per second squared is a newton in order for this to come out to something we can add to momentum, right?
Yeah.
Yeah, so that's, but they're equivalent. And in terms of, if we say kilogram meters and seconds are the fundamental units of the SI unit system, then you're correct. We could write it that way.
Okay, thank you.
Yeah. Other questions? All right, thanks everybody. You asked great questions today.